where do these dimensions exist? So in most cases, these dimensions are very compact and compactified again on around the Planck scales, right? So these are tiny. Now you'd say, wait, why don't we feel them?
हेलो दोस्तों, स्वागत है आप लोगों का एक बार फिर से रोजेंडर पर। और बड़े ही समय से मैं ये पॉडकास्ट जो है वो करना चाह रहा था, बट काफी चीजें जो है वो बीच में आ रही थी। बट फाइनली आज हम लोग जानेंगे एस्ट्रोनॉमी के बारे में और उन सारी चीजों के बारे में जानेंगे जिनसे रिलेटेड सवाल जो है वो आप लोग हमेशा कमेंट्स में लिखते रहते हो और कभी कभी पूछते रहते हो उन सब चीजों को। तो आज जानेंगे यूनिवर्स के बारे में, कॉस्मोलॉजी के बारे में और एस्ट्रोनॉमी के काफी सारे एस्पेक्ट्स के बारे में। आज हमारे साथ मौजूद हैं डॉक्टर तरुण सौरनदीप, RRI से। थोड़े समय पहले भी आईसर से थे, तो वो सारी जर्नी के बारे में आज बात करेंगे। और बात करेंगे ऐसी साइंस के बारे में जो कि अभी हम लोगों को फिक्शन के तौर पर दिखाई जाती है, बट उसमें क्या क्या रिसर्च हो रही है और इंडिया में किस तरह का रिसर्च जो है उन टॉपिक्स पर हो रहा है, सब जानेंगे। चलिए स्वागत करते हैं डॉक्टर तरुण का। तरुण सर, आपका बहुत बहुत स्वागत है। एंड कैसे हैं आप?
ठीक है, इट्स अ प्लेजर फॉर मी। बहुत खुश हूँ कि मैं आप लोगों के साथ आपको बता पाऊंगा कि मैं क्या कर रहा हूँ, हम लोग साइंटिस्ट किस दिशा में जा रहे हैं और क्या हमारी आकांक्षाएं हैं। तो
जी
मुझे बहुत खुशी है कि ऐसा मौका मिला है आप लोगों से बात करने का।
जी। So, sir, let's start with the topics that you have, like your expertise on, like your research topics. The first thing that comes is cosmic microwave background. So, sir, when we talk about when in some previous podcast, in some previous interviews, we have talked about multi-wavelength astronomy and astronomy in ultraviolet rays. So, how do we see cosmic microwave background and why is it important in astronomy?
Okay, so cosmic microwave background is interesting and exciting because it's the oldest light that you receive in the universe. So whatever multi-message astronomy you're talking about is of course great, and it gives you information from a universe which on cosmological scale is fairly recent, right? And this light comes to us when the universe was only about, we know it very precisely, very close to a half a million years old. Okay. And you have to compare it with our current age of the universe, which is like 13.6 billion years, right? So if we want to be very careful, there are very precise numbers because our measurements are so good that we can tell you exactly how old the universe was when this light came. And it also gives you a direct view of the universe as it was in the past. So if you want to compare, the comparison that is made is if our universe now is like 100-year-old person, we are looking at the universe when it was a, 1 day baby or 1 year baby, right? So it's an enormous um advantage to be able to see how the universe was, and whatever we see in the universe, we believe that the fluctuations that we see in this microwave background. So there's a microwave background, and the way to imagine it is, if you look out into the sky, as you see galaxies far away, you see them as in the past, right? I mean, because light has taken that much time, some billion years, or uh, so to come to us, right? And then if you go past that, in we have a window in the microwave regime, and where we see emission that is coming right from a plasma surface, a hot plasma surface, which is about 43 billion light years away. Okay, so light has traveled 43 billion light years to come to you from this surface. Okay.
Sir, one question I would like to just I would like to interrupt you here and just put one question. You're talking about a plasma surface, and we have heard about sun having the plasma in its core. So inside the sun there is plasma. So it it requires a very huge temperature, like 1 million degree kind of temperature for to create a plasma. So what kind what what place is this where this kind of plasma is existing?
Yeah, so
So
the universe, if you were to put a thermometer to the universe in an empty place, at this point, the thermometer will read 3 Kelvin. That is the energy density of this cosmic micro background now. But you know that the universe expands. And as it expands, the wavelength of light gets longer, which means it is at lower frequencies and has lesser energy. But if you go to this plasma surface, it was at a time when the universe was 1100 times smaller than it is now. Every distances were 1100 times smaller. Now these are really difficult things for to grapple with common day understanding, right? Because we don't see such things happening in day to day life. The closest we have is Doppler redshift. We know that something moving towards you is blue shifted, something moving away. Hence, often the picture many people would like to carry is the universe is expanding, so things are moving at a velocity and redshifting, but that's only valid in a small region around you. The actual answer to this is what Einstein told us is space-time is malleable. It changes shape depending on the distribution of matter. So if you look at Einstein's equations applied to a smooth universe, it even surprised Einstein that the solutions seem to indicate that space was expanding in time. And space expands, wavelength of light expands. And so the light, when it was emitted from a surface which was at about 3,300 Kelvin, right? The surface of the sun, from where, it's about 6,000 Kelvin,
6,000.
right? And so you can imagine one nice way to imagine the surface is it's as if you've inverted the sun and put it all around us, right? Because it's the same phenomena. So its surface is hot. It's even hotter inside because it's denser. Similarly, this plasma surface is at 3,300, but if you go past it, you go to a universe which is even hotter. So there's a phase of the universe when it is, say, millions of 10 millions of Kelvin. And that is the kind of environment you need for electrons and protons, which are, because light is energetic enough not to allow hydrogen atoms to form. It dissociates hydrogen atom. And then you form a plasma. And at those temperatures, you also are in thermal equilibrium such that you create a what is called a black body spectrum. We read about it in textbooks, but the most the closest to an ideal black body that we have is this cosmic microwave background. In fact, in the labs when we send out missions, we have to struggle hard to create a black body which is a reference which is as good a black body as the cosmic microwave background itself. So this itself, the fact that it's a black body itself tells you that the universe was at least 10 million times hotter than it was now. And to that extent, definitely this supports a hot Big Bang model, if you want to call it. I mean, the universe started from a dense, hot,
Okay,
and if you
okay.
believe in how we generated, and how we generated, and that happens. basically because you have um something called nuclear synthesis, and these are all very basic physics. These are physics that have been checked in the lab, which tell us that this plasma will be set up in the universe. And because when we are peering back, we are, peering out, we are going back in time. This plasma surface will be seen by any observer in any part of the universe, right? So if in the future, since you talked about futuristic, sci-fi, if there's some alien civilization which is at least as smart as us and has discovered the cosmic background, they will see a very similar glow from the early universe in these frequencies. Um, it tells us a lot because from 1990, so this thing was discovered in 1965 and got a Nobel Prize 10 years later. Then in 1990, there was a cosmic background explorer which established very conclusively that it's an ideal black body. So our idea of the hot Big Bang was vindicated. And also it saw tiny fluctuations in the temperature. And that was also expected because the current universe we see, I mean, you have had talks on that. So all the multi-message astronomy that you do is from stars, galaxies, superclusters, all these, but where did they form? And the imprint of the tiny fluctuations that we see in the micro background are the seeds from which these grew. And that we are very, with decades of cosmic macro background, fluctuations measurement from 1990 to now, we have very confidently established that yes, these are tiny fluctuations from which the current classical structure grew. So that's the importance of micro background. So it's like what I call is a cosmic screen, right? So first of all, it's a plasma screen. And just like you have a plasma TV around you, there's something which projects from behind. You don't see it, you see the picture there. But there's something behind. So there are two stories to it. What the picture is telling us of the story of the universe from where the microwave background was generated, but microwave background spectrum, as well as, if you go further down, what caused those fluctuations, connects to very high energy physics. And so we have, although cosmic microwave background has done amazing things in doing cosmology, it has a lot more to do. There's a lot of polarization information that we need to still extract. I mean, although we have very good polarization maps, it's only 10% of the information. And then this black body is supposed to have deviations due to known physics and could have deviations due to unknown physics, which we have very high energy. So to me, this is one singular phenomena in cosmology that stands and bridges between how structures formed in the universe, and then what was the origin of those fluctuations. And that relates to very, at this point, probably a bit speculative, but we have fairly well defined paradigm under which we understand how this will happen. And observations will, in the coming decade, I'm hoping will kind of it has borne most of the predictions of such a paradigm called inflation has been borne out. But there's one last thing that remains, which is the primordial gravitational waves, just from the beginning of the universe, beginning of when the universe started expanding, like we see now. And I think that will cap the entire cosmology story. And that's the big thing. So it's a very, very important, uh, kind of, and very singular item I find in cosmology and astrophysics, um, the micro background. And we
So,
can talk more about it. Yeah. So you can.
so large scale structure of universe and like inflation in the universe, and whenever we like hear about the Big Bang, people call it like it wasn't a bang, it was an inflation. So where does these theories came from? Like it was not a bang, it was a inflation. and universe is constantly inflating at an accelerating rate. So
Yeah.
how does this work, and how people say that that was an inflation, not a bang?
No, so the point is, again, opinions vary, but if you have an idealized model, which is what we started with, that the universe is smooth everywhere, and then use general relativity, the ideal model tells you that there will be a time in the past when the volume of the universe will go to zero, and that's called the Big Bang, right? And it's a singular point. So it's whenever we encounter infinities in physics, the general tendency is to assume that there's something more we will discover. And what we expect that will bridge that part is quantum gravity. Because our understanding of the universe in lab or the fundamental interactions in the universe, fundamental particles, the highest scales that we look at the Large Hadron Collider, maybe their cosmic ray is that are coming at much higher energy, but nothing comparable to the energies that we need for the earliest moment of the universe. So if you just, you know, ideally push the clock back, you will encounter a time when the universe was so hot that you will have quantum gravitational effects that you have to take into account. So you know that general relativity will break down at those scales. So to me, I mean, this is the point of view. I feel that as human beings, we are exploring the universe and we are kind of unwrapping what we know about the universe that we can base on confidently on physics that we know of and observations. That way, we have pushed the boundary fairly far, right? On basic physics, I told you, nucleosynthesis is, there are two independent ways we have verified that, nucleosynthesis kind of thing must have happened. So that takes you to energies of, 10 billion kind of Kelvin, right? It was as hot as that. Now, beyond that, yes, there are theories of high energy physics which we have verified to large extent. If they are true, then we can extrapolate what must have happened in the universe before that. So there must have been, quark gluons, plasma from which, the fundamental particles like protons and all were formed. That takes you further. Then you ask, there's a fond hope in particle physics that if you go to a high enough energy, all the three interactions, apart from gravitation, they become a common force. And that is encouraged because we used to look at electric and magnetic fields as magnetism and electricity as separate phenomena. Maxwell told us they are one and the same thing, right? Moving charges, create magnetism, and static charges are what we learn as electrostatics. And then going forward in the 1970s, we unified the electromagnetism with what we knew as weak force, weak nuclear force, right? Which was a spectacular thing. It was verified, and the Nobel Prize is given for that. Now, if you extrapolate that, then you need the strong force, which is what we call the nuclear forces. We hope that that will also these all three things that we see separately, electromagnetism, weak force, and strong force, will become one common force. And that energy is, you know, uh, 10 to the power of 16 billion electron volts. Just to compare, the LHC is operating at, 5 to 7 TeV, right? Tera electron volts. This is giga electron volts, and then remember you're putting 16 zeros additionally. So these are enormous energies. So we can't hope to probe them in lab, right? There won't be a, let's see. The best arena we have to test these ideas is cosmology, because in cosmology, if we take the expanding universe, go far back, we would have encountered such energies. And the question is, what are the predictions? And one of the predictions are these fluctuations that we see in the microwave background. So it's very vital to establish that the fluctuations in the microwave background originated from physics at a given energy scale. Say, what is called the GUT scale, GUT, Grand and Unified Theory scale. It's 10 to a 16 GeV. And so that is what I feel is a very exciting frontier, because it connects the cosmos to the, tiniest scale in physics, which is what we know.
जी. So, sir, when we talk about the cosmology and like quantum mechanics, so one thing that we have been hearing for a very long time, and you have used that term in uh, in explaining these phenomena also, which is quantum gravity. So what's the meaning of quantum gravity? And as we have heard that gravity depends on mass, and at quantum level there are not that, like, very little mass is available, so gravitational force will be like, if I talk about in a layman language, that will be a very little force. So why are we like talking about this thing, quantum gravity, and what exactly quantum gravity is? Are we understanding it in right way, or there's something different that is quantum gravity?
No, so in one way, it is a quest in physics, because we know that we live in a quantum world, right? That may have been some kind of a folklore in, or to the common public, it may have been some exotic phenomena, but slowly these are becoming part of life. I mean, many devices are coming up which uses quantum mechanics, very important. Similarly, the whole fact that the universe, or space time itself bends under gravity, is again something exotic for the common man. So where do you see them together? Okay. Now, for example, the latter one, this general relativity, which describes this, dynamics of space-time responding to matter. Those effects are important for the Earth, for things around the at the level of 10 to 1 minus 9. So one part in billion, or 10 parts in, or one part in 10 billion, right? But when you are using your GPS to move from one to the other, these corrections have to be made. Otherwise, flights will crash. If you suddenly, if you someone in the GPS thing said, "Oh, I don't care about GRF," these subtle gravitation effect, and take them out, there'll be disaster in common life, right? Similarly, the devices that we are using to detect these, so for your phone, cell phone, and all, see, slowly you're using devices that depend on quantum mechanics. So we know that quantum mechanics is important, right? And not only important because you're building devices on that. So these are both things. We know that the universe is quantum, and we also know there's gravitation. The biggest challenge is we have been able to quantize electromagnetic forces, weak forces, strong forces, and we have a very consistent picture of the classical electromagnetic force and how to quantize it, or the classical strong force, how to quantize. That has not happened for gravitation, and it's kind of slightly technical as to why it doesn't happen. So I won't get into that, but that remains the challenge. And there are approaches to it, because see, what happens is with gravity, the arena itself. So every other interaction, you have a space time in which you work. The space time is a background thing that is there. Then the space time itself you'd like to think of it as discrete. So there are approaches which look at atoms of space and space time, right? And various kinds, very, these are not, it's not as if, you're breaking up space time into lattice, but, there are different carbs
So
in
are
which
we
this is
are
done.
we talking about like the smallest entity of space time, like
Yes.
what we call atom as the smallest entity
Yes.
of matter?
Right.
Okay, okay,
So
okay.
same way, the scales, and this happens at the level of what is called the Planck scale. So you have to put 19 zeros, point, and then 19 zeros, and then a 1 meter. So that takes you to Planck scale. Okay, these are something that we don't expect to encounter anywhere in daylight. So even if there is something granular at that level, the normal things, or even the highest energy explorations that we have done, is not capable of exposing that. However, this has again they could have a big implication for the beginning of the universe, because we know that if it had gone to, you know 10 to the 16 GeV, it would have gone to 10 to the 19 GeV. By the way, I think I got this wrong. So this Planck size is 33 zeros, not 16. In energy, it is 10 to the 19 GeV. But if you wanted to talk about meters, it's 10 to the minus 33 meters, which is, 33 zeros, then you put a 1 and meter, right? So this is like scales that are not, explorable. Typically when you want to see small things, you have to use higher energy to see, right? So if you want to probe, say, a bacteria or something on the micron scale, we use optical telescopes. But you know that when we probe further the crystal structure of a object, we use X-rays. So, you need to probe with higher and higher energy photons. But for to probe something at 10 to the 19 GeV, you know, the energies have to be that high of interaction to probe it. And there's no way we would do it uh, in laboratory. So the universe, fascinatingly enough, I mean, if you think, it's amazing that the universe somehow has uh, a way by which naturally it gives you a window to its entire history, right?
Oh,
Starting
okay,
from the earliest energies.
okay. So here's one more aspect about the universe that has been uh, the point of discussion for several years now. Gravitational waves. So, sir, please tell us about gravitational waves. And in 2017, uh, three physicists got the Nobel Prize for this topic. So, please tell us about gravitational waves and the LIGO-India project that you are a part of. Please tell us about it.
Okay, so gravitational waves, just like, that we have electric charges, and you have electromagnetic waves. So if I charge a ruler, on your sleeve and move it
Hmm.
around, moving charges will create, you know, electromagnetic waves. So if the charges are accelerated, so when you see an antenna, what's happening is, currents are moving back and forth. So that's so. What is amazing again, fundamentally about gravitational waves is what we had before Einstein's gravity was Newton's gravity, and Newtonian gravity had no space for a traveling wave. Okay, so in technical terms, every interaction we know of has something called a radiative mode. The way it can propagate and interact. Einstein's gravitation provided that, and Einstein, in fact, a year after he uh, put his theory of Einstein's gravitation called general relativity, he also predicted that the existence of gravitational waves, and he made an estimate and he has in his paper some statement, which of course it's in the German, but Rainer Weiss kind of translated part of that in his talk. So it basically said it's not going to be of any importance because it's very tiny. The effect is very tiny, even if you take stars moving around. But in those times, you did not know that there were compact stars and compact stars correlation. So there are phenomena in the universe where the strength is of the gravitational waves generated is higher. But even then, it poses a big technical challenge. So with the best apparatus we have, which is something like interferometer, Michelson interferometer for people who are aware of it, you're looking at difference of light travel time between two arms, which are getting squeezed or stretched as the gravitational wave goes through, right? And that squeezing is at the level of 1 part in 10 to the 19. So I keep using these big numbers, but it will be attometers, right? What is technically called attometers. Okay. Now, if you want to look at two mirrors which are just moving around by that much, you know, all that requires, first of all, and the larger the baseline, the more the mirrors move in a gravitational wave. But 4 kilometers is what looked optimal. Then you have to have laser lights bouncing back and forth, and you have to detect these tiny fluctuations, right? And this was set up, as I said, Renovays had the vision to say that you can take lab size interferometers and scale it up to 4 kilometers and still make them work. And the LIGO project has took 4 decades to set it up and detect it. Uh, we got into the game in 2007, when one of the young researchers, Rana Adhikari, was visiting me at Ayuka, Pune. This was a gravitation and cosmology meeting, so there were many others. So when we discussed about the possibility of starting this experimental activity in India, I could bring together a few people and discuss it, and then in a couple of years we set up a consortium of uh, scientists interested in this, as well as people, technical people, I mean experimental physicists who are capable of understanding and setting up such a detector. And that's the story. I mean, so in 2011 we had this opportunity to set up, propose the LIGO-India project, and we are on the way. I mean, we are in construction. So that is the story. Now, why gravitational waves are important? I told you it's a unique prediction beyond Newton's gravity. I mean, you can't just improve on Newton's gravity and get the general relativity effects. Whereas gravitation, you know, gravitational waves you can't get out of that. So that's unique. It also, the fact that it is showing you that gravitation has radiative modes is a pointer to the fact when you do quantize any interaction, it's these radiative modes that you're quantizing, right? So that it's a field theory, right? And so it gives you a further impetus to say there must exist something very similar to, that like we understand electromagnetic waves having photons, there must be something similar in gravitation. Unless gravitation is, we discover is totally different. And there are people who also think of that, but uh,
So
that's what.
here's where the gravitons came from,
Yeah,
particle of gravity.
particle of gravity. But the question is, if we uh, take the path we took for electromagnetic, interactions, that's called quantum electrodynamics. You know, that path for gravitation, as the Einstein's gravity, breaks down. I mean, we can't use the same tricks that we use uh, to get it. So people have stepped back and looked at, whether we are quantizing the right objects. So there are very interesting programs. Of course, there's something called loop quantum gravity, which works in normal. three spatial and one time dimensions, and has objects that it quantizes, which are different from the kind of the basis is different. Normally, in quantum mechanics, you quantize a pair of objects, right? So here, these objects that you quantize are somewhat different from this thing, and that has led to a view of what quantum gravity may be looking like. Then there are other approaches which look at the causal structure of space-time and try to look at atoms of that, with something called causal set theory. These are all within, the three and one dimensions. There's another offshoot that is very, well established, is pushing along the particle theory aspect. And the question is, at some point, you realize that possibly thinking of particles as point objects itself is misplaced, and you think of them like stringy objects, like one-dimensional strings. But the strings, the scale is again, very small, 10 to a minus 33 meters. But okay, so you don't see that stringy character. But that's called the string theory's approach to their generatability would appear as a low energy approximation. It's not quantizing generativity, but it is, propounding a fundamental picture of how particles and emerge, right? And then that theory is quantizable. But on the other hand, to connect it to real things, first of all, it works only in if you have extra dimensions. So you have to have, additional six dimensions to make it work,
So
right?
one thing I would like to ask here, like we have heard about three-dimensional world and fourth dimension of time. X, Y, and Z are the three dimensions, and fourth is the time dimension. So fourth dimensional world is kind of imaginable. We can imagine the four dimensions, but when we go on higher kind of dimensions, like in six dimensions or five dimensions, 11 dimensions, when people talk about this, when scientists are talking about this, what do we actually mean, like the higher dimensions of space, like higher dimensions of any kind? What do we?
Okay. So I can give you an analogy. So so where do these dimensions exist? So in most cases, these dimensions are very compact and compactified again on around the Planck scales, right? So these are tiny. Now you'd say, wait, why don't we feel them? But imagine you, um, let's imagine a guitar. It has strings, right? And you can imagine, all the science that when we play it, we don't really care about the thickness of the string,
Hmm.
or you imagine a string which is, so we take it to be infinitely thin, and all the results that we do in kind of resonances and things like that, these are textbook, school textbook things. Now imagine that string was not one dimension, just a linear thing, but it was like a straw. But the straw is so narrow. So imagine a hollow tube string versus a thin
Solid,
string.
solid string.
You will not be able to distinguish unless you play it at a frequency where you excite the modes of that small scale. This is what is happening. So the strings are there, or these extra dimensions are there, but we are not probing any science which kind of leads to what we call excitations of those degrees of freedom. So if it is one linear string, then of course waves can only go on this. But you can imagine if it is actually a straw, then you will have waves going along the length. But at high enough energy, small enough wavelengths, you'll start exciting waves that are going on the surface of the straw in the other direction. Now, if that is there, then what needs to excite them are wavelengths which are of the scale of this circumference of the straw. And those wavelengths are small, which means they have very high energies. So you have to perturb that object at very high energies to be able to see that there is structure inside. Right? For example, I gave you this thing of you're looking at a crystal. When I'm looking at optical light, I don't see that crystal structure. I need X-rays to see it. Similarly, if there are additional dimensions, I need to be able to have physical processes happening at high enough energy that excite them. Now, again, I mean, maybe I'm making a habit of this. The only arena where this will play out is the earliest moments of the universe, because there we are guaranteed that we would have energies high enough, and if there are effects of that come in because there are extra dimensions, they should show up in some observation. Right? That's our fond hope.
Okay, so what is the amount of energy that
So
is required?
that's very simple, right? So I told you about Planck length. To
uh,
excite things on Planck
10 to
length,
power minus 33 meters.
33 meters. So to excite wavelengths of that scale, you need energies which are 10 to 19 giga electron volts, right?
Okay.
So that's the Planck energy. So these are all Planck energy, Planck scales. These are all related.
G. Okay, so one more question about the gravitational wave. Then I would like to move about a bit of fiction kind of thing. The topic will be a bit of fiction, but I want to know about what I want to know your take on that topic.
Hmm.
So, stochastic gravitational wave background. So, what is stochastic uh, means? Because I have heard a lot about this thing. So, what is stochastic?
Okay.
What does stochastic means, and how do we use it in gravitational waves?
Yeah. Stochastic by definition means an ensemble that can be only, you don't care about individual items of that ensemble is a collection. If you are not look at the air around me, I'm not worried about every molecule, right? I'm looking at what's the average energy of the molecule.
Hmm.
That gives me the temperature of the air. Okay, there's atmospheric pressure, which is the average motion of these molecules. The uh, so this is the question of stochastic. So where you are talking about things in terms of averages and kind of statistical averages. So that's stochastic. Now, if you look at LIGO, you know that there have been 90 events detected so far. These were individual events. So we know there was a source from which it happened. So some binary merger, and there was a well-defined signal that came out. But binary mergers, these are only few of the many, many mergers that are happening. Some probably, you know, that we are not resolving. But that gravitational wave from those are also coming, right? So that creates, I mean, so when you have good enough sensitivity, but you are not resolving each object, it gives you a noise which is like popcorn, right? So, for example, when the popcorn pops, you hear at some point there is no separate sound for every corn that is. Initially, there will be separate sounds, but then at
It
some level, it all merges
became
into a background, right? So something is happening at that. That is the stochastic gravitational wave background for astrophysical sources. And that's something that LIGO detectors may detect very soon. I mean, we are kind of homing
so
in
it
on the expected level of background.
kind
Um,
of a superposition kind of phenomena.
yeah, it's superposition and unresolved. Like, so when you have See, like when you look at a distant galaxy, you can't, your eyes cannot resolve each star. So you see a, kind of an average distribution. So it's that same thing in time. So, there are events happening. We know gravitational waves are passing through us. One thing I should mention is the universe is full of gravitation. The emission of electromagnetism is few orders of magnitude less efficient than emission of gravitational waves from
Okay,
objects.
sir. One thing that many people would ask, that if gravitational waves are kind of waves that is there in the universe, so is there a way that we physically feel the gravitational waves, or what could be the like what scales would be there so that one can feel the gravitational waves?
Yeah, so it has to be extremely strong. So at this point, all that happened. The strongest signal that we have yet measured was things, strongest signals that we have measured from LIGO, and their two mirrors placed 4 kilometers apart moved by, you know, atometers, right? So now that really, so in principle, yes, when the gravitational wave went, it actually squeezed Earth also back and forth. So the Earth also was squeezed back and forth, but that's by a very tiny amount, right? So those things are not something that we'll detect or we'll feel, other than need that. So that's why you need special apparatus, right? And even if you look at gravitational waves, we are trying to monitor pulsars, which again, if you are sitting on Earth and monitoring pulsars, pulsars are excellent clocks. When a gravitational waves on scales of the solar systems, or even bigger than much bigger than the solar system, light year scales, passes by, then it will move the pulsars closer to us or far away from us, right? So then there will be a jitter in the timing, right? And so there, what is happening is nothing is the distances between pulsar and us are changing, right? But that's also by a timing, right? So you can imagine, I mean, if you know, uh, essentially even very close to where the, if you were somewhere in the galaxy itself where these black holes merge, you know, the perturbation would not have been significant. I mean, it would have been much stronger than 10 to the minus 19. But even if you go back and look at it, it's at very small level that you will get perturbed.
Okay. So, sir, stochastic, we have talked about this term. So here I would like to add one question about.
Mhm.
So I would like to ask about multiverse theories. So it's been a very it is a hot topic in these days, because a lot of movies have been
Right.
made on the topic. But I want to know about the scientific aspects and what you people think about it. And when we talk about the multiverse theory in science, we kind of listen about the multi-world interpretation. And in previous interviews, one of the scientists told me about the string theory method. Like, it is a theory of universe and anti-universe kind of thing, like space becomes time and time becomes space. So it is the anti-universe theory. So how the multiverse is like understood, or is it a topic to talk about in science now?
Uh,
Do we know anything about?
no, so see, the point is whenever you make progress in science, there are things which you can verify,
Hmm,
but there are aspects that you cannot.
hmm,
For example, Einstein's idea that space-time is dynamic also gave rise to many spacetimes where there are closed time-like curves. right? So you can go in the past, you know. So when you're going in the future, you will go in the past and you can kill your grandfather. And there are a lot of paradoxes with that.
Grandfather paradox.
Yeah. So those we tend to keep on the side. It's not as if they are ruled out by general relativity. General relativity allows for the solutions, right? Similarly, when you go to string theory, in one version of that, for example, where multiverses have been talked about, you have, just like you have flux of magnetic field fluxes, they are more complicated fields than the electromagnetic field, that's defined by the group. And that also has something like these magnetic fluxes. Now, so there was one aspect when they really looked at arranging for those, they found that you can have a situation where the universe could start with, the what are called vacuum. Vacuum state is where, you expect a system to be in, right? But there are many, many vacuum states, right? And so the idea there is that, why is the universe? So one of the questions we ask is, why are we in the universe that we see? I mean, why are everything, all the numbers that we see, the gravitational constant, the argument there is that there are many, many. So again, big numbers, 10, 500 zeros after 10, right? Number of vacuums. So the question is, if so many possibilities, we happen to be a universe which had exactly the right numbers for all the fundamental constants, such that a universe could grow like this. And then there are arguments to show that if those numbers were slightly different, you won't really have the universe that we see. So these are, to my mind, it's more of a philosophical debate, right? And I don't want to really get into it, except to see that say that there are serious discussions on this. Because in one sense, yes, you're saying that the universe is what it is because there were many possibilities that chose the we it chose the one that we see because otherwise we couldn't have existed to see it. So it's a anthropomorphic, not anthropomorphic. It's called an anthropic idea that the universe is like this because otherwise we won't have been there to see it. But if you look at our progress of science in the last 500 years, we have been actually moving further away from trying to make us as the observer being an important point, right? And in that sense, our science has been always based on things that are falsifiable. Okay. Again, there will be people who will debate, and I'm not one who is well informed enough to take up the debate. To my mind, falsifiability was an important aspect, and particularly my research. I mean, after I started off with very exotic topics like quantum cosmology and all, but as a faculty, I have never worked on something that doesn't have a observational. In fact, I even kind of this person's style shun from things that 100 years later someone might or potentially see, right? So to me, I think things you look at things that can be tested, verified. To my understanding, multiverse is not. But that doesn't mean the multiverse idea itself has any problem. It gives you some kind of a succor. There were multiverses, even there's. I mean, this is not a new concept. I mean, to even understand quantum mechanics, there was a well-known scientist called Everett who had this multi-world interpretation of quantum
Multi-world.
mechanics because you had so it's not a new concept, right? So the idea is that in quantum an experiment that you set up, a particle could go through one path or the other, two holes, interferometry. And the question is, in we ask, okay, why did it take that path? So in some multi-world, other parallel world, it would have taken the other path. And so all possibilities exist. Um, I think that is, these are important issues. I'm not trying to say they are not, but I'm certainly not something that I worry about. And I also feel that that's not something that you should worry about until you have sufficient understanding of the science. These are nice things to talk about, but casual chat about that, I think, leads nowhere. Because you have to really understand deep down where it is emerging from. So I, for one, am not very keen to have young people, you know, just fascinated in science because thinking that is science. That is not science. That's one outcome of the scientific theory, right? That you have this, and every part of science and philosophy are not different. But you have to decide for yourself what appeals to you, and at least in my opinion, progress in science happens from this side rather than, there are, like, for example, the unification. These are all, goals that we think are nice. There are things that are mathematically beautiful, and we feel that, our theories, as they improve, they are mathematically beautiful. So, they happen to be. But, we shouldn't go so far on that line that we lose sight of the fact that the theories have to be tested. Okay. And so I think that's the extent to which I'll talk about it.
Okay, sir. Very good to hear these things about these kind of theories from a scientist. So here's we end the part one of this interview.